So this is chapter 8, part 1. We're going to be talking about reactions of alkenes. So just a brief overview. Bonding in alkenes. In alkenes, electrons in the pi bond are loosely held, right? As shown here. Double bond acts as a nucleophile, attacking the electrophile. So there's electrons in that system where it can attack the electrophile, shown here. And then carbocations are intermediates in some of these reactions because once the electrophile forms a bond, you have a carbocation with an empty p orbital. These reactions are called electrophilic addition. So in an electrophilic addition, the first step is the pi electron attacking the electrophile. Again, when you're drawing these mechanisms, you want to have full arrows in which you have the source of electrons. In this case, it's the pi bond, the double bond, attacking the electrophile so that it forms a bond. And then you have a carbocation, and that carbocation will be on the more substituted carbon. The second step is where the nucleophile attacks that carbocation. So there's another nucleophile, not from the double bond, but from elsewhere, coming in to quench that positive charge, generating your product. So in terms of additions, this is from table 8.1 or 8-1s from your textbook. You can have hydration, in which you're adding water across the double bond, hydrogenation, which we talked about, in which you're adding hydrogen. This is called a reduction, so you're reducing the double bond. You can do dihydroxylation, in which we're adding a peroxide across, and this is an oxidation. You can do an oxidative cleavage, in which you change that double bond and make it into, in this case, ketones or aldehyde, depending on what's attached to your carbon. You can do an epoxidation, where you take that double bond, add an oxygen to generate an epoxide. Halogenation, which we've talked about, in which you have halogen as a dibromine, diatomic bromine, diatomic iodide, etc. onto it. This is also an oxidation. Halohydrin formation, also an oxidation in this way, in which you have hydroxide and a halogen being added on. You can have just HX addition. This is a hydrohalogenation. And you can have cyclopropanation, in which you have CH2. Addition of HX to alkenes. Step 1, protonation of the double bond. The protonation step forms the most stable carbocation possible. In the second step, the nucleophile attacks that carbocation, forming the alkyl halide. And then in terms of the types of HX that can be added, you can have HBr, HCl, HI in terms of additions to alkene. So in terms of the actual mechanism, here's the addition of HBr to a double bond. So the first step, again, nucleophilic attack from your source of electrons, full arrow, taking off that proton, forming the bromide. So now you form the most stable carbocation, and then you have that bromide serving as your new nucleophile, quenching that positive charge to have this addition occur. In general, the stability of carbocations, as you know from earlier chapters, is tertiary is more stable than secondary, is more stable than primary, and then methyl. So an electrophile will add to a double bond to give the most stable carbocation in the intermediate. In terms of the regioselectivity, it obeys what is called Markovnikov's rules. In Markovnikov's rule, the addition of a proton to the double bond of an alkane results in a product with the acidic proton bonded to the carbon atom that already holds the greater number of hydrogens. In an electrophilic addition to the alkene, the electrophile adds in such a way that it generates the most stable intermediate. So if we look at Markovnikov's rule in practice, here's the addition of HBr to an alkene. First thing again, nucleophilic attack, H. H goes to the secondary carbon, because then it would form a tertiary carbocation, which is more stable. In this case, here's an example of nucleophilic attack. Bromine gets kicked off. Where H is added to the tertiary carbon, this does not happen because the secondary carbocation is not as stable as a tertiary carbocation. So the acid proton will bond to carbon 3 in order to produce the more stable carbocation. Here's another example in which we have cyclohexene, 1-methylcyclohexene. So you can have the alkene pluck off that hydrogen, kick off the bromine so that you generate a carbocation. The carbocation that you want to generate is the tertiary carbocation shown here, so the hydrogen will add to this. So your product afterwards, the bromine will quench that positive charge, will form this. So again, the positive charge is on the most substituted carbon, that is favored, and the less stable carbocation is not formed. So show how you would accomplish the following. So this is problem 1. Convert 1-methylcyclohexene to 1-bromomethylcyclohexane. So here's 1-methylcyclohexene and you're adding HBr. You're adding HBr in Markovnikov orientation, in which the H goes to the least substituted side. So here you go. I'm going to draw it out. You have your arrow, and then you have the electrons from that bond go to the bromine. This will generate an intermediate that looks like this, in which you have a positive carbocation over here, right? That's the more, that's the more substituted carbocation, and the H will add onto the least substituted side, allowing for Markovnikov addition. And then the Br minus that's floating in comes back as a nucleophile to quench the charge so that you generate this product. Free radical additions of HBr. So in the presence of peroxides, HBr adds to an alkene to form the anti-Markovnikov product. This is crucial. So in the previous case, with just HBr alone, you have Markovnikov products. But when you're adding peroxides to the system in the presence of HBr, you have the anti-Markovnikov product. Peroxides produces free radicals. As a result, only HBr has just the right reactivity for each step of the free radical chain reaction to take place. The peroxide effect is not seen, so this is also important. So even if you add peroxides, you don't see that with HCl or HI, because the reaction of an alkyl radical with HCl or HI is strongly endothermic. So let's look at an example of free radical initiation for peroxide. So the peroxide, and we've discussed this, I guess, in chapter 4 in one of your problems that we discussed in the problem set 4. You have, in the presence of heat, right, these are half arrows now forming the radical peroxide. And then the hydrogen is abstracted from HBr. So, look at that. Propagation steps. Bromine adds to the double bond, forming the most stable radical possible. So you're going to have, in this case, a mechanism where you have electrons from the bromine, right? So these are half arrows, electrons from the double bond, and then the electron from the double bond now being the one electron going to the carbon. So it's on the secondary carbon instead of the primary carbon, because the bromide just added to the least substituted side. Then you can have hydrogen abstraction, in which you have, again, half arrows are being shown, right? And then bromine to generate the bromine radical. So remember, use half arrows in these reactions, especially because these are free radical reactions that we've discussed in chapter 4. So as a result of that, you have anti-Markovnikov stereochemistry. It's really important, right? So the first thing you do is you have bromine radical attacking, so, right, to form the bond so that you form a radical on the most substituted carbon side, so it's a tertiary radical. That tertiary radical forms faster just because it's more stable. So in general, in terms of stability, tertiary radical is more stable than secondary versus primary versus methyl. Radical adds to a double bond to give the most stable radical in the intermediate. So let's look at problem 2, where you're looking to convert 1-methylcyclohexanol to 1-bromo-methylcyclohexane. So this synthesis requires conversion of an alcohol to an alkyl bromide with the bromine atom at the neighboring carbon atom. So this is an anti-Markovnikov product, which could be formed by radical catalyzed HBr to 1-methylcyclohexene. So 1-methylcyclohexene is shown here. So if you do a reaction with HBr and peroxides, right, it'll generate the Br radical. The Br radical will add in where it adds in over here to the least hindered side so that you can form a stable radical, tertiary radical, and then that will be added on, the hydrogen will be added on there. And now in order to get to this as a starting material from 1-methylcyclohexanol, you take 1-methylcyclohexanol in the presence of acid, right, and heat. That will protonate this so that it's water, remove it so that you have a carbocation, and then eliminate so that you form a double bond, methylcyclohexene, and then we can move forward. So we went from knowing how to generate this from here and then going backwards to the first starting material. So yeah, so that's how we solve the problem. So the two-step synthesize is as follows. You start off with 1-methylcyclohexanol. In the presence of sulfuric acid and heat, this will undergo E1 elimination, and then you have peroxides and HBr, which is addition, but this will give you the anti-Markovnikov product over here. In terms of hydration of alkenes, that's pretty easy. You can take an alkene in the presence of water and some acid to generate the alcohol. Now this obeys, the addition obeys Markovnikov orientation. Addition of water to a double bond forms an alcohol. Addition follows this Markovnikov rules. This is the reverse of a dehydration of alcohol, which we saw in the previous problem where we added H2SO4 to dehydrate to form an alkene. If we look at the mechanism for hydration, so you're adding water that's in some acid. As a result, you're going to have protonated water. So the first thing that you're going to be doing is you have your nucleophile, right? Take that proton, generating water and generating the carbocation. Carbocation is on the most substituted carbon. Then you have nucleophilic attack of the water onto that carbocation so that you generated this protonated alcohol, and then you take water and you deprotonate that so that you generate the alcohol and hydronium. So we get back to this hydronium. In terms of orientation of hydration, Like I said, it obeys the Markovnikov's rule, so the proton will add to the least hindered side so that you can generate the carbocation. Again, nucleophilic attack from your source of electrons, plucking off that proton, that's going to go on the least hindered side, giving a more stable tertiary carbocation. There are rearrangements that can happen. So in the presence of your alkene, in this case sulfuric acid, and water, you can generate the OH adding over here as the product. So how does that happen? That happens through what is called a methyl shift. So when you generate the carbocation, so the first step is you're going to take this, and I'm going to show, sorry, please bear with my not so perfect handwriting here. Here's that hydronium ion because you have sulfuric acid and water. So the first step is nucleophilic attack, right? And plucking off one of these protons, making this neutral, so that you generate, right, the carbocation. The carbocation, so it will go on the least, the hydrogen will go on the least hindered side, which is this side. As a result, you have a carbocation right here. Now, this is not as stable as if you did a methyl shift. A methyl shift is when you have the whole methyl group, this blue group, which I'll highlight here, move over to this carbon right here, so that, sorry, that's supposed to be a full arrow, so that now the carbocation has shifted to the tertiary, more stable. And as a result, from here, you can have then your water that you have remaining. Sorry, here's water. I'm making it blue. I'm sorry, it's not perfect. Here are my electrons. Okay, so this will come in, quench that charge. You'll generate a protonated version of that intermediate, and then it'll deprotonate from the water, taking off that proton, which I don't have space, but you can do on your own. So here, methyl shift after protonation will produce the more stable tertiary carbocation. The other reaction that's an important reaction is oxymercuration demercuration. Oops, sorry, I still have the pencil drawn in. So here you have, in the presence of your alkene, mercuric acetate, water, you have the addition of the mercuric acetate and OH occurring, and then in the presence of sodium borohydride, it'll replace the HGOAC with a hydride, and it'll add in the Markovnikov orientation. So oxymercuration demercuration allows for Markovnikov addition of water to the double bond, milder conditions than direct hydration, and no rearrangements or polymerization occurs using oxymercuration or demercuration. Reagent is mercury acetate, which I've discussed, which dissociates to form this positive mercury acetate. The mercury acetate is the electrophile that adds to the pi bond, right? So then the double bond will go and attack this. The intermediate is a 3-membered ring called the mercurium ion. So this is something you'll have to know. And overall, the addition follows. So in the mechanism of oxymercuration, again, your source of electrons is your double bond. It's your nucleophile, which attacks the HGOAC, but then you have electrons from that Hg come down to form this mercurinium ion shown here. It's important that you note this in your mechanisms. Then the water, as your nucleophile, will attack the most hindered side, break open that, so that you generated the OH2+, and now the HGOAC is on the most hindered side. And then you have OH2, water, coming and plucking off that extra hydrogen so that you make the alcohol. And now you have still the HGOAC on the other carbon. In terms of stereochemistry, Water adds to the more substituted carbon to form the Markovnikov product, so that's what this I've discussed already. Water approaches the mercurium ion from the side opposite the ring, so it's an anti-addition. So here's the ring, so it's on the other side of that ring. It's an anti-addition, and so now you generate your organomercurial alcohol. There's a demercuration, that means removal of the mercury. So in the presence of sodium borohydride, which is a reducing agent, it'll simply replace the hydride with replace the HGOAC with the hydride so that you generate your alcohol. So, so the hydride from the sodium borohydride replaces the mercuric acetate. Overall reaction gives a Markovnikov product, important, with a hydroxyl group on the most substituted carbon. So if we look at an example of oxymercuration, demercuration of 3,3-dimethylbute-1-ene, first thing you do is you form the mercurinium ion shown here, right? Because of the nucleophilic attack, so let's draw that in. Nucleophilic attack here, and then the electrons from HC come down, generating HGOAC, mercurinium ion. Attack of the water goes to the more hindered side, and then removal of H, so that you now have your product where you have your OH on the most hindered side and your mercuric acetate on the least hindered side. Then in the presence of sodium borohydride, you have replacement of this with the hydride, so you generate the butanol. Really important thing is that this reaction does not undergo rearrangements. So it does not, because there's no carbocation intermediate, unlike the H2SO4 and water reaction of forming alcohols from alkenes. Alkoxymercuration, demercuration. So if the nucleophile is an alcohol, right, ROH instead of water is added, then ether is produced. So you can have ROH shown here coming and attack the most hindered side, so now you have ROH. Another ROH will deprotonate so that you have RO, so now you're generating an ether, sodium borohydride to replace the mercuric acetate with an hydride. So let's look at problem 3. Show the intermediates and products that result from alkoxymercuration, demercuration of 1-methylcyclopentene using methanol as the solvent. So here's your 1-methylcyclopentene. In the presence of mercuric acetate, you have that reaction, right? Electrons go here. Sorry, this is supposed to be a full arrow. And then electrons come down as well to form that mercurinium ion. And then you have attack of the alcohol. It's methanol is in the solvent. That will attack the most hindered side, having the HGOAC go on the least hindered side. It's a trans-intermediate, right, because it's going on the opposite side. It's attacking from the opposite side of where the mercurium ion is. So it's an anti-addition. Then you have removal of the H from the alcohol. That was our methanol that was attacking, so you generate the product. And then in the presence of sodium borohydride, you simply replace this to generate the 1-methoxy 1-methylcyclopentane. So note that the hydride that's replacing the HGOAC doesn't change the stereochemistry. That's really important. You can also do hydroboration of alkenes. Hydroboration oxidation, you start off with an alkene, shown here. In the presence of borohydride and THF, you have addition of the hydrogen and the borane right on top of the double bond. In the presence of peroxides and hydroxide, you have replacement of the BH with OH. This is anti-Markovnikov, really important. So in the previous case, you have Markovnikov addition. Now you have anti-Markovnikov, and the stereochemistry is syn. In the oxymercuration, demercuration, it's anti. So H.C. Brown of Purdue discovered that diboranes add to alkenes in an anti-Markovnikov orientation, forming alkylboranes, which after oxidation give anti-Markovnikov alcohols. He received Nobel Prize in 1979. So if we look at how diborane is generated, you have tetrahydrofuran, which is shown here, in the presence of diborane. This will form a bond, right? So you have B2H6, and so you have one BH3 being added on via nucleophilic attack from the tetrahydrofuran to the diborane. So let's try to do this so that you can see. So here's B. Sorry about this, it's not perfect, but it's hard to do this on an iPad here. Okay, right. Okay, so now you're I'm going to change it to blue. Attack on that borane, diborane. Here's your arrow kicking this guy out so that you generate this complex, right? The borane THF complex. So this borane THF is the commonly used form of borane that is used for this reaction. So now, once you have that, you essentially have the BH3 come in. BH3 will come in. Syn, which is at the same side, so they're coming in. I'm going to show you that they're coming in and reacting on top, where you have the BH2 part adding to the least hindered side, the H part adding to the most hindered site. And so this is your transition state generating the product shown here. So again, boron adds to the less substituted carbon, hydrogen adds to the more highly substituted carbon, and then this orientation places the partial positive charge in the transition state on the more highly substituted carbon. So this is what's key. Stoichiometry of hydroboration, you have BH3, so you can have H and BH come and add, right? So that you add H on one side and BH2 on the other side, but you can have you have these other two BHs adding, so you can have two of these add, another one add to this alkene, and a third one. So you have 3 moles of alkene reacting with each mole of BH. So in terms of the remainder of this reaction, so once you have BH2 being added on, this gets replaced by OH in the presence of peroxide and sodium hydroxide in water, so that you have oxidation of the alkyl borane with basic hydrogen peroxide, producing the alcohol, and the orientation overall being anti-Markovnikov. If we look at the stereochemistry of hydroboration, like I said, they're coming on, this HBH3 is coming on one side. So here is the least hindered side with the boron, and the hydrogen to the most hindered side, developing a partial positive charge on that side. Here's your transition state in parentheses. Again, double dagger. Sorry, this is my double dagger. So now it's coming from the bottom side, and then when you add hydrogen peroxide and hydroxide, this simply replaces with hydroxide. So this addition, when they're both coming up on the same side, is called syn addition. So when the boron is oxidized, OH will keep to the same stereochemical orientation in the final product shown here. So you can do oxidation of trialkylborane. Here's hydrolysis of borate ester. So once you have the additions occurring, then you can have OH come in, nucleophilic attack, kick off one of the ORs, and then in the presence of water, O gets protonated. So let me draw that arrow for you. Will get protonated from the hydrogen of H2O. So I'll draw out H2O. Sorry, it's going to be clunky, but here you go. And then electrons go here so that you generate OH minus, the alcohol. So you can do this 2 more times. So let's look at problem 4. How would you convert 1-methylcyclopentanol to 2-methylcyclopentanol? So 1-methylcyclopentene in the presence of step 1, borohydride and THF, and step 2, hydrogen peroxide and OH, will generate the syn product, right, in which you have 2-methylcyclopentanol. It's going to be trans respective to the CH3 and OH, but it's syn addition. Then if you do look at 2-methylcyclopentanol, that is a result from the synthesis of the pure trans isomer. This stereochemical result is also discussed in this section in your book. 1-methylcyclopentene is the most substituted alkene that results from dehydration of 1-methylcyclopentanol, so shown here. So in the presence of H2SO4, it will dehydrate, right? It'll pluck off that proton, kick off that hydroxide, forming the water, forming the carbocation here, and then the water will come in as a nucleophile and form the double bond. I'm not showing those steps, but you can do those on your own. So then that's how you would generate that. Another problem is norborane molecule labeled with deuterium is subject to hydroboration oxidation. Give the structures of the intermediates and products. So here's norborane with a double bond, BH3 THF. So it can go on the outside face, which is the exo, or the endo, which is on the bottom side. So if we look at the face that would happen, the addition would happen on the outside or exo face of the double bond, because that is preferred over the endo. And once that happens, you have H and BH3. BH2 is going to be on the most hindered side, but in this case, they're symmetrical, so there's no difference. And then in the presence of H2O-OH, you're going to replace that BH2 with OH. So just in general, going into here is very difficult, and it's less accessible versus going through here, and that's why this exophase is preferred. Addition of halogens. Here's your alkene in the presence of dihalogen, Cl2, Br2, and sometimes I2. And then this will usually add in the anti-addition. This, when you form these a halide next to one another, these are called vicinal dihalides, and this is anti. So let's look at the mechanism. In terms of the mechanism, you have the alkene attack, right? Here's your source of electrons, here's your nucleophile, attack, and form a bond and then kick off that X. It forms what is called a helonium ion. Just like the mercurium ion, you're now forming a helonium ion. And now the X, the remainder X, in this case the halogen, will then attack from the backside and kick off that. So the intermediate is called a helonium ion, and then you have anti-attack from the other side. So if we look at the stereochemistry of the halogen addition, again, you're going to have nucleophilic attack. This gets kicked off, form the bromonium ion, and then the bromide will attack on the opposite side of the face, right? If it came on the bottom, it's going to come on the top side of the face. This backside attack assures anti-stereochemistry. So anti-stereochemistry is generated. And you can generate this as well as the enantiomer. In terms of stereospecificity, here's cis-2-butane and trans-2-butene, or cis-butuene and trans-butuene. bromonium ion is formed, right? So you have nucleophilic attack, and then you have backside of attack, so that you generate this. You have both enantiomers of this being generated, so you have 2,3-dibromobutane and the other 2,3-dibromobutane. If you start off with trans system, you do the same thing, nucleophilic attack, kick off, and then this goes on the bottom. You generate the meso 2,3-dibromobutane. Bromine test for unsaturation. You can add Br2 in carbon tetrachloride, and it forms this dark brown color to an alkene. Color quickly disappears as the bromine adds to the double bond, which is the test tube on this side. If there's no double bond present, the brown color will remain. And so the decolorizing bromine is the chemical test for a double bond. So that's showing the addition of bromine and forming a vicinal dibromide. So I'm going to stop here.